Let's talk about reaction energy diagrams now, okay? This is theory. No, this doesn't have to do with the labs at all. Or this lab, anyway. Well, it does, but we're not going to apply it to this lab. I'm trying to keep it simple in terms of just making the calculations and interpreting the results to give you a clear and justified answer on the quiz tomorrow. That's what we're working on for that. Okay, this is something a little bit different, kind of a different. It's still talking about change in enthalpy. Okay, but it's going. The ice cream lab is all about physical change, and now we're back to chemical change. These energy diagrams actually work for both chemical and physical, but we won't get to that too much. Yes.
We're doing all the work for the lab tomorrow.
We're doing all the quiz to give you the opportunity to eat the ice cream you made.
We don't have to redo that on the lab, do we?
Before? No. All you need in the lab, you won't even need your lab notebook, really. I will have you put your procedures in your lab notebook, but it'll be very, very brief. Fill up the side with ice cream mixed to this point. Fill up the other side with salt and water, and this much, and shake, rattle, and roll. Okay? Let's reaction energy diagrams. Let's talk about what reaction energy diagrams. So this is going to be the first quadrant of a Cartesian plane. Okay. All the graphs we do in here, first quadrants. Well, maybe not all of them, almost all of them. Huh? Isn't that the first quadrant? Oh, okay. All right, what we want to look at then in terms of, this could apply to physical changes. We're going to talk about it as it applies to chemical changes, okay? So if I start out with chemicals that we'll just simply call A, and I do a chemical reaction, I end up with chemicals we'll call B, going from A to B, okay? So A represents any and all reactants. It might be one reactant, or it might be 3 or 4 reactants, okay? So all the reactants are A. And B stands for all the products. So then overall, what we have on our x-axis down here is the progress of a chemical reaction. Okay? Now last week, I did a whoosh bottle demonstration. Whoosh bottle.
Oh,
yeah. And that whoosh bottle, was that exothermic or endothermic? Was it endothermic? Well, I got a difference of opinion here. Well, now you're just guessing. He says it's exo. How would you know if it's exo or endo? Did it release energy? Did it release energy? Well, kind of gained, but we'll talk about that. It mostly released energy, so that's an exothermic reaction. So this is for an exothermic reaction we're working with here.
I accidentally did something a lot like that.
Okay. All right, now, if it's exothermic, it gave energy to the surroundings, right? Yes? That's what an exothermic reaction does. It gives energy to the surroundings. Where did the energy come from?
Outside.
The video we saw earlier, he said there's only a fixed amount of energy in the whole universe. And you cannot gain energy in the universe or lose energy in the universe. You can only move it around from system to surrounding. Okay? So where did the energy come from? The system. All right, now, more specifically, it's a chemical reaction. What is the system where that energy is stored when you have a chemical reaction? Where is that energy stored? The bonds between the atoms. Okay? In a chemical, in any compound, there is energy stored in the bonds between the atoms. In any chemical compound, there is energy stored in the bonds between the atoms. In any chemical compound, there is energy stored in the bonds between the atoms. Yes. Yes. In any chemical compound, there is energy stored in the bonds between the atoms. That's the enthalpy, exactly. That is what we call the enthalpy for a chemical compound. It's stored in the bonds between the atoms. There are actually other kinds of enthalpy, but that's what we're talking about here. Okay? The bonds between the atoms. All right? Huh?
What is that you said?
Enthalpy?
Yeah.
Enthalpy. That's what all that delta H stuff is. That's the enthalpy.
That water is awful. Yeah, it is.
Well, be glad you got some.
But doesn't it, or did it not take energy from outside?
What do you mean?
Like, it took the energy from when you lit it.
Okay, we'll get to that. Hold that thought. But overall, we had energy coming out, right? So where did we get the energy from? That we ended up with it being hot on the outside, warmer on the outside, right?
Yes.
Where did the energy come from? No, that is the surroundings. We are the surroundings. The bonds between the atoms. Okay?
Yeah.
There are bonds between these atoms and the reactants. What do we start with? What two things do we react together in the whoosh bottle?
Fire and...
Fire's not a chemical. What? Ethanol? We reacted ethanol with what? Okay, combustion requires the same thing it has to react with. All combustions look the same. Look on the chart y'all gave you. Those equations have a lot of things in common. You've got to have oxygen to create combustion. You have to have a fuel. Ethanol is the fuel. Oxygen is the thing that reacts with the fuel. So you have to have ethanol and oxygen. Okay? What products did we get? Water. What else besides water? Well, you could say fire is a product. There's one other chemical, though. What other chemical do we have as a product? You always, in a combustion reaction, you always have the same product. Carbon dioxide and water. Okay? Are there bonds in water? Are there bonds in carbon dioxide? Are there bonds in ethanol? Are there bonds in oxygen? So we got bonds over here and bonds over here. Where did we get the energy from? Yes?
Oh, I have a question.
About this?
Yes.
Hold that question. Where do we get if we have bonds on the left and bonds on the right, and we've got to get energy out from the bonds, where do we get the energy from? The bonds. Still the bonds. But there must be a difference in the amount of energy. Okay? Alright. In the reactant side then, is our initial stored energy in the bonds going to be higher on this side or higher on this side? On the left, where the reactants are. If we get energy out, had to come from somewhere, and there must be more energy in these bonds than in these bonds. So let's put it there. Here's our beginning energy, and here's our ending energy. How about that? How does that work for you? Okay? Now, about that match you mentioned. Every chemical reaction must have something to get it started. Okay? Every chemical reaction must have something to get it started. And it's called activation energy. So our match that we lit is what it took to get it started. So we initially put extra energy into it. Okay? We initially put some extra energy into it. And then we can get all that energy out.
So would that make the match?
No, Match is not the catalyst. The match provided the activation energy to start the reaction. Once the reaction starts, it produces its own heat, which continues to activate the reaction. Okay? But not all chemical reactions require a match. Anybody ever put vinegar and baking soda together?
Yeah.
Did you have to have a match to get it started?
Yeah.
What? Yeah, I did, didn't I? I just put vinegar and baking soda together in the balloon demonstration, didn't I? Yes. Yes.
What happened?
You can also go to what's it called? Oh man, Cracker Barrel and get a Coca-Cola cake. Okay. Yes.
Have you ever seen like a YouTube video on the Sprite and banana challenge?
No, but can we let's just hold that thought, okay? I want to stick with this right now, okay? Guys, focus here, focus here. We got off track here. I know that was interesting and everything, and we're talking about CO2 coming from the Sprite and all that, but let's stay right here right now, okay? All right. Now, every chemical reaction, yes, even baking soda and vinegar, requires activation energy. Where did that energy come from? Well, there's energy, potential energy, all around you right now, because the molecules in the air are moving, because the molecules in your body are moving, because the molecules in the water that makes up most of your blood is moving. Even the molecules in your desk, they're sitting there wiggling. We talked about that last week, right? How the molecules are always moving, or the atoms or structural particles, if it's ions or atoms, they're always moving. Okay? So that movement of those particles provides the potential energy to activate some reactions. Some reactions don't need outside influence, like we needed a match to start the whoosh bottle. Okay? But regardless of whether the energy to start the reaction is provided from just the environment, or you have to stick a match to it, you always have to have activation energy. So the difference in energy, the increase of energy, when we lit our match, that's how much extra energy we needed to start the reaction. The increase in energy required to get that reaction going, that's called activation energy. And it's that amount of energy represented by that arrow right there. So in the video we saw earlier, somebody asked the question about absolute zero. At absolute zero, there is no activation energy available in the surroundings. So vinegar and baking soda won't react together at absolute zero. In fact, it'll stop reacting long before that. Okay?